All right, the purpose of this video is to get into hypothesis testing for regression, and I want to cover confidence intervals and hypothesis testing for beta 0, beta 1. So again, remember that we have this population model lurking out there somewhere. We don't know anything about it, right? And we dive into our population. We take a sample of n subjects, and we use our sample data to calculate our sample model. So we'll have a sample slope, sample intercept and a sample slope. And this sample slope can be used to estimate the value of the population intercept. Okay, the sample intercept can be used to estimate the population intercept. The sample slope can be used to estimate the population slope, as I've stated right here. Now, why do we use technology? Well, sometimes the calculation of beta 0 and beta 1 can get pretty ugly. Even though I look at this and that falls right smack dab in my comfort zone, it may not fall in your comfort zone. Now, luckily for us, there are easier ways to calculate beta 0 and beta 1. Again, our coefficient estimates of, to calculate B0 and B1, our estimated regression coefficients of beta 0 and beta 1. So there are a couple of easier ways. We can always calculate B1 by just taking the correlation coefficient times the standard deviation for our y's divided by our standard deviation for our x's. I may demonstrate that. I haven't decided yet. And once we get B1 here, and again, I can't stress enough, this B1 is estimating beta 1, and this B0 is estimating beta 0. But we can take the mean of our y's minus the beta 1 that we calculated over here times our mean of our x's to get the B0, which again is the estimate of beta 0. Now, the steps that we'll follow, I want to keep the calculations out, the extreme calculations out of the instructional unit for this lesson, but I do want to go through and demonstrate the steps. So the first thing we'd want to do is we'd want to calculate B0 and B1. These values appear, and I'm just going to use technology. I may show you how this all works out. Again, I haven't decided yet. We need to calculate what's called SE. That's a standard error of the estimate. I'll show you how to find that using StatCrunch. The next thing we do is we calculate the standard error for the sampling distribution of B1, state the null and alternative hypotheses, calculate the test statistic and p-value, make a decision, calculate the confidence intervals, and then on the back I'll show you that we have some rules for actually using our model to make predictions. So let's get to it. Over on the left, you'll see that I have a rather large data set. I think it would be kind of interesting to examine the relationship between the weight and the highway miles per gallon. So since the weight of the car comes first, you know, when a car comes off the assembly line, it has a weight, and the miles per gallon is actually established later. It wouldn't make sense for me to have my dependent variable as weight, because the dependent variable depends on the x, so it will be my independent variable, weight will. So the way I carry this out, come down to regression, go to simple linear, and I want my x variable to be weight, and I want my y variable to be highway miles per gallon. Now, the hypotheses, we're going to set up the intercept equal to 0, intercept not equal to 0. Standard form, the slope is going to be equal to 0, the slope not equal to 0. We'll get into confidence interval later. Really, that's about all we need at this time. There's a lot of cool stuff down here, but unfortunately, I don't have enough time to teach it all to you. So we get our shoot. We get our values. So first of all, our estimates for B0 and B1. So we get that multiple places. We can get our B0 right here and our B1 here, or we can get the same estimates right here and right here. And as you would expect, our relationship is negative, so the correlation coefficient is going to be negative because you would expect heavier cars to have lower highway miles per gallon. So my estimate, my B0 is going to be 58.86, and my B1 is going to be negative point, what is that, 0.075. Is that good enough? Next thing, we calculate the standard error of the estimate. The standard error of the estimate comes under the estimate of the error standard deviation. So this turns out to be 2.514. And this just gives us an indication of the standard error of our residuals, which I talked about back in a previous lesson. And it may be that you need to go back and watch a few videos from that lesson. Don't spend a lot of time and go through all of the videos unless you, of course, you need it. But just to get familiar with the framework of regression, you may need to revisit that. Calculate the standard error for B1. Well, that value is right here. That's under the standard error for B1, which is our slope. So that would be how many zeros there? 3 zeros, so 0.0057. Next thing, state the null and alternative hypotheses. The only thing we state for here is for our beta. So we want beta 1 equal to 0 versus our alternative beta 1 not equal to 0. For the sake of this class, I think we're going to live in the two-tailed test only. I don't think I'm going to get into any directional type tests. Calculate the test statistic and the p-value. Again, we have tunnel vision on our slope. We don't really care as much about the intercept because it's not that interesting. So the test statistic would for the slope would be negative 13.21. And the corresponding slope, to 3 places, which is probably what you would round to on my stat lab would be 0.00. Now, assuming that we're testing at alpha equal 0.05, and again, that would be stated, but nevertheless, any of the alpha values, this p-value would fall below. So then we would make a decision that we reject H sub O. So by rejecting H sub O, we can assume that a linear relation exists between the weight of a car in miles per gallon. Now, huge, okay, get this. This is important. I want to kind of tattoo this one to the brain, put this in flashing neon lights in your notes. Just because, let's say that we end up failing to reject H sub O, it doesn't mean that a relationship between the two variables doesn't exist. It just means that a linear relation between the two variables doesn't exist. For example, let me just go off script a little bit here. We could have a relationship between X and Y that looks something like that. Now, does a linear relation model our data well? No, it doesn't. Linear relation would not be appropriate there. But we may consider some sort of quadratic regression that would fit and model the data well. So again, the techniques that I'm teaching you here pertain to a linear relation between the variables, not, more generally speaking, a relationship. Now, the confidence interval may be given over here. No, it's not. So to get the confidence interval, I'll need to go up to options and go to edit. And instead of selecting the hypothesis testing information, I need to come to the confidence interval. Let's compute. And we have tunnel vision on the 95% confidence interval for the slope. So it looks like to me this is negative 0.086 up to negative 0.0063. And we get a visual, and it's easy to see from the visual that the straight line that we've modeled our data with does appear to be linear. It looks like it fits the data well. And so it's no surprise that we rejected the null, right? The next thing we may want to do is, as I've stated on the back, is make predictions. Now, one little caveats to making predictions is we never want to make predictions outside the bounds of our data. So my X in this case is weight, and weight ranges from, well, let's go grab it and see. Well, that just gives us a range, doesn't it? So we're going to have to work a little harder for that. So let's go to columns and let's just go to the min value and let's grab the max value. All right, so the min is 2468. Max is 4949. All right, so someone comes to you and says, all right, I know you've been doing this work on predicting weight from, I'm sorry, predicting miles per gallon from weight. And your model is 58.86 minus 0.0075. Predict the miles per gallon for this new Hummer that I bought that is 5,500 pounds. Well, your model was built on these bounds, right? We don't know what happens above 49.49 because we don't have data up there. We don't know what happens below 2468 because we don't have data down here. So we could not predict the miles per gallon when the weight equals 5,500. This is actually called extrapolation. Extrapolation's bad. We don't make uh, we don't make predictions outside the bound. It'd be kind of like going into a kindergarten class and gathering some data on kindergartners, right? Young kids, right? And creating a model, and then going into a nursing home and using our model to make predictions of people in nursing home. It just wouldn't work. That's not the population for which we built our model. The population we built this model is for weights from 2468 to 4949. Anything outside the bound would not be appropriate. Now, if the weight, for example, is say 3,000 pounds, then we can proceed, right? So the miles per gallon that we would predict would be 58.86 0.86 minus 0.075 times 3,000. Let me pop that in the calculator real quick. And I get a predicted miles per gallon of 36.36, which isn't bad. When I'm posting this video, gas prices, Russia has, to give you an idea, because you may be watching this video 10 years from now, who knows? But Russia has invaded Ukraine, and gas prices are going up in the United States quite significantly. So that's where we are. That's where I am today. All right, gang, let's dive into a little more. I want to show you, if you're just given these values in an output, I want to show you how they are actually related. So since we've got this, let's just pull up. Well, let's go over and grab this and grab the simple linear regression, and let's edit, and let's go back to the test of hypothesis. Okay, and I will show you how these things are related. First of all, we can come up with the t statistic. So for the slope, the t-stat, the test statistic, which in this case is negative 13.21. The way that's actually calculated is the test statistic is the beta 1 minus the beta 0 over the standard error for beta 1. So my estimate for B1 is negative 0.0075. I'm hypothesizing the beta is equal to 0. And the standard error is right there. So point, again, I don't want to mess up, point, what, 3 zeros, 5, 6, 7. Now, if we put that in our calculator, so this will get negative 13.22, actually 23. So we're off just a little bit. Well, we're off because of rounding. If I had taken this out to 7 or 8 digits and this out to 9 or 10 digits, then I would get the more of an exact value for the test statistic. And the same thing for the intercept. Take the estimate minus 0 divided by the standard error, and that will give us the test statistic. Now to calculate the p-value, so when t is equal to negative 13.21, the p-value calculation, remember the degrees of freedom are n minus 2. We're given the degrees of freedom right here, 46. So that tells me that the sample size has to be 48. And of course, I can go to what we got. So degrees of freedom, 46. So I'm calculating this p-value in the t-distribution. Degrees of freedom equal 46, and I need the area to the right of 13.21 and to the left of negative 13.21 because I'm conducting a two-tailed test. So go to the calculator, test statistic, degrees of freedom. Again, you can go above or below because this value is going to be the same as this value. And I get one of them and multiply by 2. So I'm going to go just below negative 13.21. and I get, a very small number. This is in scientific notation, so the e to the negative 17 says I need to move the decimal place 17 places to the left. So you can imagine how small the number is. So the p-value here to 4 places would just be reported to 0.00000. So I pretend I said 4 zeros. All right. All right, that's about all I'm going to do. This is kind of cool where we get into the regression analysis, get into an ANOVA. The only time this really matters is when we get into multiple predictors, where we have maybe we're trying to predict uh, the miles per gallon for maybe weight and number of cylinders, and whatever it may be. Then we not only have coefficient diagnostics, so we have a diagnostic for each coefficient for each predictor. We also have a model diagnostic, how well comprehensively, collectively that our predictors are doing in predicting whatever we're trying to predict. All right, gang, that's all I got.